Power Integration's 60-watt Flyback converter is designed to supply two independent outputs, 5 volts and 24 volts. The system is based on the InnoMux2-EP IMX2-353F H4 automatic chip and offers high efficiency greater than 90%, precise voltage regulation, and a wide input voltage range. This solution is ideal for industrial and appliance applications thanks to its safety features, overvoltage protection, thermal protection, and a heatsink-free design that uses only the PCB for cooling. It's a very compact, efficient, protected, and versatile power supply that demonstrates the potential of Power Integration's PowerUP technology and intelligent multi-output management via InnoMux. The InnoMux family includes the industry's first power devices to feature a 1700-volt GaN switch. The official datasheet is a rich source of information on the device and is highly recommended for careful consultation and reading. The Flyback architecture enables the design of a single-stage multi-output converter with a wide input voltage range from 70 volts DC to 1000 volts DC and outputs of 5 volts at 2.5 amperes and 24 volts at 2 ampere. Its full load efficiency exceeds 90% across the entire input voltage and load range. The converter is extensively protected. The switching power supply is intended for industrial and appliance applications and uses the IMX2-353F H415 InnoMux2-EP chip. It features two constant voltage outputs and can deliver a maximum power of 60 watts with an input voltage up to 1000 volts DC. It is characterized by high efficiency and precise output regulation thanks to InnoMux2's power multiplexing control algorithm and a high level of integration.
Let's first examine the primary side. Capacitor C1 is connected in parallel to the input and acts as a ripple filter. The transformer's primary is connected between the input and the drain of the MOSFET integrated in the InnoMux2-EP IC. The voltage across this winding is rectified and filtered using diode D1 and capacitor C48. Resistor R66 limits inrush current. Overvoltage protection on the primary side is implemented using Zener, diode V R3 and series resistor R37. Capacitor C2 is used to set the primary peak current to a standard level of 1.85 amps.
Now let's examine the secondary side with a somewhat detailed but important analysis. It is powered by an internal regulator. The secondary side of the InnoMux2-EP IC sends a request to the primary side controller to initiate a switching cycle via pulse on an isolated channel. The SR pin drives the synchronous rectifier and MOSFET when the transformer delivers energy to the secondary circuit. Before the secondary discharge ends, the SR MOSFET gate voltage is lowered to prevent premature turnoff. A special mechanism called zero voltage switching significantly reduces switching losses, minimizing turn-on losses of the primary switch, especially at high input voltages. To ensure low output ripple voltage, a PI filter composed of capacitor C10, C26 and inductor L2 is used. The low ESR capacitor C10 in the first stage attenuates ripple current, while capacitor C26 minimizes switching noise. Ceramic capacitor C28 eliminates high-frequency noise. Rectification for the CVHV output is provided by the SR MOSFET and diode D3. Low ESR capacitors, C14 and C15 filter
the CVHV output energy. Inductor L5 is placed between C14 and C15 to further reduce ripple and noise at the CVHV output. The RC snubber network, consisting of R6, R75, and C19, dampens high-frequency oscillations on the SR MOSFET. Another RC snubber, R76 and C56, damps high-frequency oscillations on MOSFET Q2. Finally, a third RC snubber, R13 and C9, reduces high-frequency voltage transients on diode D3. The CV1 output voltage is regulated by R35, R54, R10, and C51. Loop compensation required due to L2 is provided by R9 and C27. The CVHV output voltage is set by R7, R56, R8, and C5. Loop compensation required due to L5 is provided by R72 and C54. Let's try to identify the main components. First, examine the top part of the circuit. In the center of the board, we can see the transformer. The datasheet provides detailed characteristics. On the left, we see the input connector in parallel with the high voltage capacitor used to reduce ripple. At the top are two 4.7 nanofarad ceramic capacitors connected in series to ground. Capacitors C14 and C15 filter the CVHV output voltage. Additionally, the PI filter composed of capacitors C10, C26 and inductor L2 ensures low ripple at the output. Connector J1 provides the VHV and CV1 outputs, along with their respective grounds. Now let's examine the bottom part of the circuit. Diode D3 is used for signal rectification. Q2 is a 40 volt, 36 ampere N-channel MOSFET. Q1 is another N-channel MOSFET rated at 100 volts and 60 amperes. VR1 and VR2 are TVS diodes that suppress dangerous high voltage spikes. Finally, U1 is the main component, the InnoMux2-EP Flyback switching IC. Now let's build a circuit that allows us to obtain a voltage of approximately 325 volts DC starting from the 230 volts AC mains. The schematic shows a classic AC-DC converter using rectification of the AC current. Extreme caution should be exercised due to the high voltage involved. Here is the complete circuit to be connected to the power integrations converter. The resistor plays an important role in discharging the capacitors when power is removed. Now let's connect the voltage booster to the power integrations kit, respecting the correct polarity. Always proceed with the maximum caution. First, we measure the AC input voltage of 230 volts AC. Then, switching the multimeter range to 1000 volts DC, we measure the output of the first converter. The voltage is 315 volts, which is perfectly within the operating range of the power integrations kit. Lowering the DC range to 200 volts, we measure the VHV and CV1 outputs. Placing the ground probe on GND, the tester reads almost 25 volts on the VHV output. Then we measure the CV1 output, where we read a voltage of about 5 volts. Note that no load was intentionally connected to the output.
Keep in mind that the device's efficiency is very high and at full load CV1 equals 5 volts at 2.5 amps and CVHV equals 24 volts at 2 amps. Across all line voltages 300, 500, 800 and 1000 volts DC, it exceeds 90%. The official datasheet meticulously reports all waveforms related to the switching nodes at various points in the circuit.